and even with that reinforcement, you still have to comply with those upper and lower filling limits for a conventional LNG carrier. So I think what you were trying to say to me was, if we kept one tank, or if we kept 3 tanks full and just reinforced one tank, and we could have one tank at maybe 50%, that's not possible. Even with the reinforcement, you cannot have the tank of a full-size LNG vessel at 50% full.
So what's the solution?
At the moment, the solution is for full-size LNG vessels, they have to either virtually completely fill the tank or empty the tank. And if you think about the LNG industry, historically, the LNG industry originated really with projects. And the project would involve a loading port, a company to transport the LNG, and a discharging port. And usually all of those companies were partners in the overall project. The ship would only fill up at the loading port, and it would always empty out at the discharge port. And by and large, that is still the case today. But we now have a spot market where we might have vessels that are trading on slightly different irregular patterns. But even so, if I charter your LNG vessel, I'm going to basically want to fill it up with as much cargo as I can, to fill it completely full, because otherwise I'm wasting money. I only make money on what the vessel carries, and I have to pay you for your vessel a fixed amount every day anyway. So I want to fill it up, and when I get it to the discharge port where I want to sell the cargo, then I want to empty it out. So for a conventional LNG carrier, sailing around with half-full tanks isn't really a particular desire. So it's not really something that you want to do anyway, because of the nature of the business.
Yes, and something else, you said that when the tanks are empty and the vessel is ballasted, the tanks are compressed because of the hydrostatic pressure of the
There's a certain force on the hull structure because of the ballast water pressure, yeah.
Yes. In this case, probably if we increase the temperature of the LNG tank, and
you're thinking about trying to equalize the pressures? Yes. No. Partly because the pressure would be too great, you couldn't do that. But secondly is because it's not so much a global pressure. Remember there's a diagram I showed you, it was a coloured kind of CAD type diagram, the N-type diagram, where between the pressure was bulging between the stiffeners. So even if you try to pressurize your tank in the way that you're thinking, you wouldn't be able to push down in each of those little areas because the membrane is resting across all of them. So it wouldn't be able to just press down on those. But so ultimately the answer is no. You can't pressurize the tank internally to counteract the pressure of the water created by the ballast water. Interesting idea though. Good idea, but no, you couldn't do it practically.
Thank you.
I'd like to ask a question as well. Well, as you mentioned, for the LNG vessels, most of the tanks are fully filled or fully empty. Anyway.
I understand.
Yeah. But in the case of FLNG, such as the Prelude or any others, most of their life, the tank will be partially filled.
Yep.
So my question would be, one of the major issues in sloshing has to do with the ratio of the filling over the length of the free surface, and I expect that the length, what we saw was a cross section, and the length would be larger. What would be a typical length to breadth ratio of a membrane tank?
I'm trying to think. Off the top of my head, I can't think of the values of the length and breadth of a tank. But if I can send an email to answer that question later, for sure.
Yes, thank you.
To go back to what you were starting to maybe think about with the sloshing and the FLNG, the difference there is the FLNG or even the regas vessels, they're not sailing at sea. They're in open water, so they are subject to some physical motion, but not as much motion as a vessel that's actually sailing at sea, which is subject to much greater motions. So with regards to the conventional vessels that are coming in to discharge alongside those vessels, again, they have to be a little bit careful about, when the tank is half full and the motion of the vessel, but generally speaking, they're not in particularly exposed ocean areas, so they're not exposed to massive amounts of motion. And the vessels like the FLNG and the regas vessels, they've had their tanks reinforced based on the amount of motion that's expected with the tank at the worst level, let's say 50% level, and because the vessel's not sailing, then the tank is reinforced sufficiently to be able to withstand that. But it's an important design consideration. Okay, so I have a limited amount of time left to me now, and so what I'm going to try to do is give you a little bit of information about the Mark III system and the NO96 system. In the presentation material I've left behind, there's a separate two additional presentations, which I don't have time to cover today, which shows you some of the stages of the actual construction in the shipyard of these membrane systems. But I think it'd be most useful, best use of the time we have available, to look at the actual elements, how these two membrane systems are made up. So let's try and do that. Let's see, working here. Okay. So we're looking at the Mark III system first of all. I'm going to explain to you the general concept, elements that make it up, and I'm going to mention to you some of the evolutions of this system that you may not have heard of, something called the Mark III Flex, and one that you almost certainly won't have heard of, called the Mark V. So I'll see if I can go through that. So this is the nice photograph inside a conventional LNG carrier again. Remember, I keep saying that this is a full-size LNG carrier, so we have this classic shape of a tank, this prismatic shape, but we can make this a rectangle or a box, anything you like, if it's going to be a fuel tank on an LNG fuel. Okay, so a feature here, which will become more apparent in a minute, is this kind of the material of this primary membrane. It's often referred to as a waffle plate. So here's a piece of the primary membrane. So in the Mark III system, primary membrane is made of a material called stainless steel. So a particular grade of stainless steel, 304L, and you can see that it has these folds or corrugations in there. Now you can probably guess the reason for those there. It's because when you cool that down to minus 160, it's going to contract. So to absorb that thermal contraction, the sheets of stainless steel are folded in this particular way, so that when we cool it down, all of the contraction is absorbed by these folds. So the actual stress on the material itself is very low. Okay. Now, we've seen already that the membrane system has to have a secondary barrier. And in this Mark III system, the secondary barrier is made not of stainless steel, it's made of a different material, something called triplex. And triplex is itself kind of sandwich, which is made up of in the middle, aluminium foil, a very thin sheet of aluminium foil with a kind of glass cloth top and bottom to the sandwich. So this is called triplex, and it acts as a secondary barrier. I'll show you where it's located in a moment. The insulating material is reinforced polyurethane foam, often referred to as RPUF because it's easier to say than reinforced polyurethane foam. Now, because of the stresses, the flexing and the stressing on the hull that we talked about earlier, if we just had blocks of polyurethane foam, there's a good chance they'd crack as the hull is flexed and stretched. So it's reinforced with glass fibre to prevent it from cracking. So this is a typical kind of example of how it's put together. So on the top here, this is a piece of the second. This is like a piece of the insulation here. The primary membrane would fit on the top here, and I'll show you that more clearly in a moment. But this is the insulation itself. So we have some foam, some polyurethane foam. The grey is the secondary barrier, triplex. Then we've got some more foam, and then we've got a plywood sheet on the top with some stainless steel strips attached into that, which allows us to then weld stainless steel primary membrane onto that. Okay, so I'm going to explain that in a bit more detail with some nice diagrams in just a moment. But dimensionally, the thickness of this insulation system is about 270 millimeters. So the secondary insulation, so here is your inner hull. Here is the secondary insulation, which is about 170 millimeters thick. Here's the primary insulation, about 100 millimeters thick. And then we've got the triplex secondary barrier at this point and the primary membrane on the top here. Okay. So, with all of these containment systems, one of the key things from a manufacturing point of view is to make them as uniform as possible. So what I mean by that is we want as many standardized components as possible, because that keeps the cost down in terms of manufacturing, and it makes the installation easier. If you're just installing multiples of the same thing, it's easier to train people. If you have many, many different components to install, it becomes more difficult to train people and more complex and expensive to install. So as much as possible, we minimize the elements that make up this system. And that's what I'm going to just show you now, some of those elements. So the panels, which are used in what's called the flat wall area, all these areas here, all the flat surfaces in this tank, we refer to as the flat wall area, and they're made up of these panels. We can see the panel, you saw that just now. Let's split it apart. So each panel is a sandwich, which has a plywood base, polyurethane foam, secondary insulation, 170 millimeters thick, sheet of triplex, that's our secondary barrier in case the primary fails. Then we've got a thinner 100 mil thick piece of primary insulation, and once again a piece of plywood board on the top of that, which allows us to attach the primary membrane onto it. So all of those components are bonded together with glue in a factory where it's manufactured, bonded together, and it's held under a certain pressure, certain temperature and humidity for a certain number of hours, and that is a panel, and we use multiples of those panels in all of the flat areas in the tank. So those are the elements there. So here in this diagram you can see these are all the flat panels here. So you see them on the bottom of the tank, you see them on the transverse bulkhead here at the fore and aft end of the tank, and you see them on the chamfer wall here. So they're all the same. They're about 1 point, forgotten the size of them now, doesn't matter, it might come up in a minute. But those are the flat panels, okay? Get the idea? Where we come to the joining between two of these flat surfaces, we refer to this as the dihedron. So we have some 90-degree angles here, and we have these angles on the chamfers. Depends on the exact design of the vessel, but it could be 135 degrees is pretty typical. But they can be any angle you like. You can make them anything you want, or they could be just rectangular. So this is the dihedron. This is where the corners are located. So these panels are slightly different now, and I can split one of those apart so you can see how it's made up. So here you can see that we have a secondary insulation here. There's a plywood base behind there. Plywood base behind there. And then we've got our triplex here. So these are made up of two elements which are joined together, and of course there's a bit of a gap between there. So we have this piece of secondary membrane, which is then bonded onto there to cover the joint, and then we have the primary part, the primary insulation here, which is slightly different. Instead of being lumps of polyurethane foam, it's actually got to be a little bit stronger, and so we use blocks of plywood with 6mm thick stainless steel plates joining them together. Here you can see one of them here. Okay? So that's what goes together in this bit here. So when we put it all together, those are the dihedrons which run along here and along here. Wherever we get two flat surfaces coming together, we have one of those. Now, in these little corner pieces here, we actually have the joining of three flat surfaces together, and this is called a trihedron. So same sort of idea, but slightly different construction. So now there are 1, 2, 3 faces to this, and if we split it apart, again, it's not too difficult to see. We've got polyurethane foam for the secondary barrier. We have 3 separate pieces of triplex here, so we have another piece that's folded to go across all of those. Now, because of the way that fold is, you'd end up with a kind of a sharp point So there's a bit cut out of that, and then a small scab which is stuck over it to complete the seal on there. And then we've got more pieces with plywood blocks here and a stainless steel plate to give it additional strength in the corner. So that's where they're located here, where we get the three faces joining together. So those are the main components of that system. Now, when we put it together, there's a little bit of a problem here because we have some gaps between the panels here, and of course the secondary membrane itself has got some holes in it and gaps in it, so we've got to fill all those in as well. So what we do is, at the construction stage, when all of these elements are in place, we then run strips of triplex across all of these joints, and they're all glued in place. As much as possible, all the long lengths of this are done by automatic machines. Using machines minimizes human error and increases the continuity, the consistency of the quality. In the corners and in the areas where the machines can't get, then people have to do that. And the guys who do the manual bonding in the corners are very highly trained. They have to test all of these parts when they've been bonded down. They go around with a vacuum box, and there's several tests that are carried out. This is a little diagram showing you the triplex. I mentioned to you that it's got a thin film of aluminium foil, and it's surrounded on each side by some glass cloth. So that is the secondary barrier. And if we just go back a touch here, and once we've glued all of these in place, there are still some gaps here in the insulation between here. So we've got to fill in all of these gaps now to complete the insulation. So that's where this bit comes in here. And this is referred to as a top bridge pad, and it fits in between all of those panels now. We fit them all in here so that we end up with a smooth surface. All the insulation is completed, and all we have left to do now is install the primary membrane onto the insulation system. So those are the elements that make up the system. Here's the primary membrane, a stainless steel waffle plate, and you can see that it's welded onto the strips of stainless steel that are part of the top of the insulation system. And then, of course, each plate overlaps the next one and is continuously welded all the way along. All of the welding, except right in the corners, is again done by machines to get a greater quality control. And so that completes the primary membrane then. So we've got our primary membrane, and then we've got the insulation system beneath it. Part of that insulation system contains the triplex secondary membrane, and then we're in contact with the inner hull. The method of attaching those panels onto the hull, they are, in this system, they are physically bonded. They are glued onto the hull. So to glue them onto the hull, they use ropes of mastic, which act as, they do two things. One is to physically bond it to the hull, and the second thing is to spread the load onto the inner hull, because you maybe you're aware, maybe you're not aware, when you build a ship and you have great big blocks of the hull are put together, the surface of the steel is not nice and smooth and flat like that tabletop. It's a bit up and down, it's undulating. So the thickness of the mastic ropes underneath those panels varies to absorb the gap depending on the undulations of the steelwork. So it fills the gap, as it were, and it also transfers the load onto the hull as well as bonding it onto the hull. Now, we mentioned earlier about reinforcements, okay? So there, for this system, you can reinforce the insulation panels, and or we can have some reinforcements for the actual primary membrane itself, depending on what we need for this particular vessel, given what the vessel's going to do and where she's going to work. So as far as the insulation system is concerned, I just mentioned the mastic ropes that fit underneath. Now, it's a bit hard to make them out, but these are the mastic ropes underneath, so the inner hull would be here. Basically, for the insulation here, what we can do is increase the, or reduce rather, the pitch at which these are located. So the more of them we put in, then the greater the load bearing, the more reinforcement we've created. As far as the primary membrane is concerned, there are two levels or two ways we have of reinforcing the primary membrane. Those corrugations that you saw, the folds in the primary membrane, can be strengthened themselves by creating little ribs within them, and that gives them a greater structural strength to resist the motion of the liquid that might be moving around in the tank. Okay? If we feel that we need even more reinforcement than that, then we can locate small plywood wedges underneath those corrugations. So again, that gives them great resistance to pressures pushing on them created by the liquid moving around in the tank. So those are a couple of ways that we can reinforce that system. Now, if this works, you will see a brief animation showing the way in which these come together. So here's the inner hull. Now there are some studs that are located on the hull to allow us to locate the flat panel. So here's the mastic ropes that go on the back of those panels, and there they go down onto the inner hull. So we secure those down, and then we fill in the gap between. There's the triplex to close over the gap, so that completes our secondary membrane, secondary barrier. And here we're showing the reinforcements being put in here, so the reinforced wedges as well. And that would complete the membrane system. You can find that little animation if you want to view that again. If you go to GPT's website, that's gpt.fr, then on their website, have a search around on there, look at the products, I think it is, and you'll find it within the products section.
Yeah, we would like to pass this
sure.
students because they cannot see this.
Okay. Yeah, that's where you can find it, no problem. Okay, now, I mentioned to you that there's a couple of evolutions of this technology, and one evolution which is currently in use, and they are building ships with it now, I think they started 2013, is called the Mark III Flex. And there were two drivers behind this. One was to increase the strength of the insulation system, and the other was to increase the insulation performance. Now, there's a kind of a bit of a dichotomy here. You can't increase the strength of something, of your insulation, and at the same time improve its insulation performance. If you increase the strength, generally, you are increasing the material composition of that element. Now, if you increase the material composition, then you're increasing the heat transfer, and you're going to make the insulation property worse. Or you can go the other way, and you can make the insulation property better, but not have such good strength. But you can't generally do both things at the same time. You have to choose. So anyway, the Mark III Flex, the project was to offer both of these options, and then the ship owner could decide what they wanted. Okay, so the way it worked out is that they increased the density of the foam to give it additional strength. But because we'd given it additional density, we had to make it thicker. So to give the same boil-off rate. So that was the strength option, which nobody's taken up. Nobody wanted to do that, it turned out. Having increased the thickness of the insulation, what we could do then is keep the same foam density, so it's no stronger, but it's thicker, so that means your insulation performance is better. So the boil-off rate reduced from 0.15% per day, that's the maximum guaranteed, in practice it will be lower, down to 0.1% per day. And this is the option that's being used on the Mark III vessels that have been constructed in the last couple of years. So just to clarify that, I showed you this diagram earlier. It showed you the dimensions, and I said to you that the total was 270 millimeters thick, and the secondary was about 170 millimeters thick, and the primary was 100. So what's happened here is, again, to make things as manufacturing-wise, to make it as simple as possible, we've kept this bit the same, so that's still 100 millimeters thick. But this bit has increased from 170 to 300 millimeters thick. So you've increased the thickness of the insulation and therefore improved the insulation properties of that system. Yeah.
What's the weight you have per meter?
The density of the foam that's used here is about 120 kilograms per cubic meter. If you wanted to have the other option that no one's taken out, the density of this foam was increased to give you greater strength, but that was again the reason for having to make it thicker to still give you that same 0.15% boil-off rate. I'm not sure what the increased density was going to be actually. Nobody's opted for that choice. All the ship owners have opted for going for the same density of foam with the increased thickness to reduce the boil-off from 0.15 down to 0.1% per day. It's giving them a better insulation performance.
But the whole build-up of the first body, the second body, all these instructions, do you have any working figure as weight, kilograms per square meter for this?
So like the panels themselves?
Yeah, for the whole construction.
The whole tank, well, that's hard to say because it depends how big the tank is. I'm trying to remember for the panels are about 3 meters by 1 meter. And I think they're about 100, I've got a feeling, a figure of about 120 kilos per panel is in my mind, but I'd have to check that.
You can check because
sure,
given that you have the same instruction, you should have some. It's pretty much standard. You should have some.
They're pretty standard.
Kilos per,
absolutely. I can find that out for you. Yeah. No problem.
Thank you.
No problem. If you take the same hull size and you make the insulation thicker, then the cargo carrying capacity must be less. Depends how big your tank is, but you can calculate it. If you say that the thickness of the insulation is now increased by 130 millimeters, then for any given size and shape of tank, you can calculate how much less volume you've got. But that's the trade-off that you have to decide.
Yeah, but you lose less from the boil-off, which is 30% less.
Exactly. And it's what you deliver is what you make your money on normally. So it's an interesting calculation. You could, in theory, we could make the insulation 2 meters thick and the boil-off rate would be much less. But then what you deliver and so on. So it's like an optimizing. It's trying to find the balance between those parameters, which gives us a commercially viable solution. And that's a big part of this design game here, is to come up with optimized designs that compromise between all these different factors and give you the best possible benefit of all of them. But as you recognize, as soon as you change one, you influence another. So it's quite interesting. Now, so far we've talked about the Mark III design and this variation called the Mark III Flex. Now, there is something else that if you keep watching the newspapers and the shipping press, you will hear about in the not too distant future, but you heard it first here. There is a new design which GTT have developed, and it's currently going through approval processes with the classification societies now, and it's called the Mark V. Now, your first question may be, what happened to Mark IV? Because we've jumped from Mark III to Mark V. Well, you may know, I didn't, but in the Asian countries, the number 4 is an unlucky number. Just like here in the West, we consider 13 to be an unlucky number. So in Asian countries, the number 4 is the equivalent. So rather than upset anybody by naming it Mark IV, they diplomatically chose to call it Mark V. So that explains what happened to Mark IV. Now, let's skip through to just look at the diagram. So the original idea behind this was actually aimed at the LNG fuel tanks. But it's now it can be used for that, but it's now being developed for full-scale LNG carriers as well. But basically, we've taken the Mark III concept, so we've got the same polyurethane foam, we've got the same stainless steel primary membrane, but the thing that's different here is we've replaced the triplet with a different material called Invar. So instead of gluing all of this triplex down, we're now going to use a metallic membrane which is welded. So you could even argue that provides you with a greater integrity because there's no bonding now, it's all welded. And so it's the same as the Mark III, except we've replaced the triplex with Invar. Now, because Invar is going to shrink a little bit, there has to be some compensation for that. And so in this system, compensation is very small reverse corrugations in the Invar. So it's a little bit like the stainless steel, but smaller corrugations in there, because Invar has a much smaller coefficient of thermal contraction than stainless steel does. Okay. So look out for that. You're going to start hearing more about that in the shipping press, I would guess, by the end of this year and into next year.
I'm wondering what type of welding do you use in order to weld very thin sheets of...
I think it's. I think I'm correct in saying, I'm not an engineer, but I think I'm correct in saying it's all TIG welding without filler metal. But again, the welding technology that goes into all of this, again, there's been a lot of development of that over the years, lots of testing to make sure, all fatigue testing and all kinds of testing that's been done on that. But I think it's TIG welding without filler metal. Okay. But don't quote me because I'm not an engineer. Okay, so does that give you a reasonable idea about the Mark III system? Okay. So what I'm going to do now is give you a similar kind of overview, but for the NO system. Okay. Hopefully. Oop. Okay, here we go. Okay. Right. So, similar idea for the NO system then. I'll explain the NO system and I'll explain to you at the end a recent development, which again, if you keep watching the shipping press, you'll hear a bit more about a development of this NO96 system. So we'll start again with a nice picture. You've seen something like this already. This is the inside of the full-size LNG tank. Once again, you can make a fuel tank any shape you like. But here we have the standard prismatic shape and the pump tower at the aft end. So the NO96 system, same basic principle of the membrane that we talked about earlier in the morning. But in this system, we have two metallic membranes, primary and secondary. In fact, they're identical. And we have two layers of insulation. And the insulation is made up of plywood boxes, which are filled with an insulating material. It's a little bit different. Now, the primary and secondary membrane are made out of Invar, the same material I just referred to or mentioned in the Mark V. So, in this NO system, the Invar is laid out in strips or strakes, which are 500 millimeters wide, and they run the whole length of the tank. The edges of the Invar is just turned up just a little bit here at the edge. And I'm not sure if we see it in this presentation, but they're basically attached to the plywood boxes and welded together. Okay? There are no corrugations in this. This is actually attached at the fore and aft end of the tank to the hull of the vessel, which is completely different to the Mark system. In the Mark system, there is no direct attachment of the membrane to the hull. But in the NO system, the membrane is directly attached to the hull, and I'll show you that in a moment. So I mentioned that the insulating system here is very different. It was blocks of polyurethane foam in the Mark system, but in the NO system, it's made up of boxes, plywood boxes, which are filled with an insulating material. Now these boxes, to make them strong, have internal bulkheads inside them, and they're filled with an insulating material. Now up until about 2 or 3 years ago, the insulating material was always perlite. So perlite is it's like a volcanic rock. It's a bit like popcorn in the sense that the rock is heated up until it kind of explodes like popcorn, forms tiny little granules, and each granule has lots of little air holes within it, and it's very light, and it's a very good insulating property, and it's coated with silicone, so if LNG gets into it, or even water gets into it, it's not really affected. But that gave a boil-off rate of around about 0.15% per day. So to reduce the boil-off rate in more recent years, they've replaced the perlite with glass wool. And that's also very light and has slightly better insulating properties. So once again, we have a flat wall area, and then there's some other components that make up this system. So let's just have a quick look at the flat wall area. So a little bit like the Mark system, all these flat bits here we're referring to as a flat wall area. So here's how it looks. If we took a cut through, here would be your inner hull. Here is the secondary insulation box. And you can see its internal division, and here it looks like it's filled with the white perlite, but now it's glass wool. And then we've got the box has a plywood lid to it. There are little strips, these are called tongues of invar, which slot into grooves in the top of the box, and that allows us to attach those strakes of invar, which remember are 500 millimeters wide, and then they're all welded together to form a leak-tight secondary membrane. And when that's done, we pile more boxes on top of that again, and it's basically a repeat process that both the secondary and the primary are virtually identical. There's a few millimeters difference in the thickness of the secondary, but overall the total thickness of that insulating system is about 500 millimeters, more or less. So it's a little bit thicker than the MARC system. So if you took two identical hull sizes and you fitted one with the MARC system and one with the NO, the one with the NO system has a slightly smaller cargo capacity. So you might notice, or I'll point it out to you, that we have the internal bulkheads run in one direction on the secondary and the opposite direction on the primary. So that's good for the structure, for the strength. So remember that all the weight of the liquid on here has to pass down through that structure and onto the inner hull. And once again, we use mastic ropes here to transfer the load onto the inner hull. And it's not very apparent, but those mastic ropes line up with all of those bulkheads inside that box. So all the load is transferred directly onto the inner hull. Now, a big difference between the MARC system and the NO system is the fact that I said to you with the MARC system, the panels are actually glued onto the hull. So as the hull flexes, those panels all flex a little bit with it. Now, these plywood boxes are not as flexible. We cannot glue the plywood boxes onto the hull because as the hull moved, as flexed, the boxes would crack. So we have a different method of attaching them. And in fact, it's not very clear, but there is a sheet of, it's called craft paper, this sort of olive-coloured material underneath the mastic ropes here. And this is specifically to stop the boxes sticking to the hull. So here we're using the mastic purely to transfer the load onto the hull. The way we attach the boxes, we'll come to that in a minute. So actually here you can see, it shows you, this will be a very poor piece of steel work, but it gives you the impression that the steel of the inner hull is not flat. And here you can see how the mastic ropes fill the gap so that they're spreading the load from the box onto the inner hull. So we talked about this earlier, about the pressure from the ballast water here. And so because we're not going to glue the box onto the hull, we have to have some mechanism that both attaches the box to the hull but allows for that global and local deflections in the hull. So the way that we achieve that in the NO system is with this device here, which is called a coupler rod. And the coupler rod, it starts at the bottom here with a couple of baits, which is welded onto the inner hull. And then we have this rod that fits inside here. And this little arrangement here, which I'll show you in the next slide, there are some spring washers in here which give it an elastic capability. Let me see if I can show you. So first of all, here's the coupler base. Remember, this bit's welded onto the inner hull. Now the first thing is, the coupler rod has a degree of articulation within that coupler base unit, so it can flex a little bit to side. So that helps absorb some of the movement. But remember, as the hull flexes, and particularly with that ballast water movement, the hull is going to be pushed up between the stiffeners. So here, if you look in this diagram here, you'll see in a moment, as the hull gets deflected between the stiffener, watch what happens to the spring. Can you see? So imagine the ballast tank is now being filled up with ballast water, and so it's slightly deflecting the hull structure. And if I just wind it back, let's try it again. You can see how that spring washer arrangement is absorbing the movement of the hull. So all the time our box remains attached to the hull, but it's not subjected to exactly the amount of stress that the hull is exposed to. Now on top of that, the requirements for the strength of the hull are greater for an NO vessel than they are for a MARC vessel. Stiffness of the hull is slightly greater for an NO vessel than it is for a MARC vessel. So the amount of steel work that goes into the hull of an NO vessel is slightly greater than the MARC vessel. Not a lot, but there's a little extra stiffening goes on in there because of the limitations of the boxes. So here, hopefully you can see, we've got the box coupler, which is attached to the hull. This arrangement here fits over, this bit's referred to as the cleat on the edge of the box, and it's basically pulling the box down onto the hull. It's a bit hard to make out, but the secondary membrane runs across the top here, and there is an arrangement where we attach basically a small version of that coupler through the secondary membrane and into this main coupler here. So basically this is holding the primary box on, so the primary box is held on by this piece, which in turn is linked to the coupler and onto the inner hull. So that coupler doesn't just hold the secondary box on, it holds the primary box as well. So there we have it. There you can see the arrangement, and when we install it, of course there's small gaps between the boxes, and we fill those with insulating material as part of the construction process as well. Okay, so that's the boxes. The strips of INVAR we have here. Now, INVAR has a very small coefficient of thermal contraction. Now, in the longitudinal sense, we'll see in a moment that the INVAR strips in this direction are attached to the hull of the ship. So when they shrink and contract, there's a certain pulling on the inner hull. Okay, so I'll show you how that's attached in a moment. But in a transverse sense, across this way, then the amount of shrinkage is quite small. So actually, the edges of where they're turned up here are capable of absorbing that amount of movement. You might see that in the slide in a moment. This diagram here is simply showing you how we attach the secondary barrier onto the plywood box. So in the top of the plywood box, in the lid, you can see this T-shaped groove is cut in there, and there is this little L-shaped piece of INVAR which slides into that groove, and that's referred to as a tongue. And then each side of the tongue, we have our strakes of INVAR here, and then these are all welded together in a continuous seam welding, and so we get a leak-tight barrier, and that's the mechanical attachment of the membrane onto the secondary boxes. Now, in fact, in this case, the primary boxes then sit on top of that as well, so they also help to keep it in place. Okay, so I mentioned about the way in which we attach the membrane to the hull, and I said to you in the transverse sense here, the little turned up edges of these strips are capable of absorbing the thermal contraction, and this little animation shows that quite nicely. Can you see there, as we cool the membrane down in a transverse sense, because the shrinkage of this material is so small, that little bit of flexing that's permissible here is sufficient to absorb transverse thermal contraction. But in the longitudinal sense, we are actually attaching the membrane onto the hull. And so in order to bridge the gap between the membrane and the hull, we use this piece here, which is called an INVAR tube. And I'm going to show you another slide of that in a moment, which will show it a little more clearly. But basically, our secondary membrane comes along at this level and goes through here and is attached onto the inner hull at this point here with something called an anchor bar. And the same thing happens at the primary level across here. And then in the vertical sense, it happens in the same way as well. We've got the secondary and the primary. I think you'll see that a little more clearly in just a moment. So that's what we're going to actually look at on the next couple of slides here. This is what we refer to as the transverse corner, where we have two surfaces coming together. Now, because of the shapes of the tanks, in the tanks 2, 3 and 4, these will all be 90-degree angles. In tank 1, because of the shape of the forward part of the vessel, the angles are slightly different, but the concept is the same. Diagrams I'm going to show you show the 90-degree version. They're a little easier to visualize. So here is that INVAR tube, which links the membrane, connects the membrane onto the inner hull. And remember, this is only found at the forward and the aft end of the tank. Side to side, we don't have to worry about it. So this is the diagram, I think makes it a little bit more clear, I hope. So here, this is probably the easiest one to look at. Here is my cofferdam bulkhead at the aft end of the tank, let's say, and here's the inner hull, the bottom. And I have these bits here are called anchor bars, which are welded onto the inner hull at these locations. I now fit my INVAR tube wing into here, And these are insulation boxes that fill up the holes here. But you can see that the secondary membrane will come along here and be welded on at this point. And because this is then welded onto the anchor bar, we now have a connection between the secondary membrane and the inner hull. And the same happens here at the primary level. And then if we look in the vertical sense, it's exactly the same. Here we have the secondary, and here we have the primary. Now, actually, something I didn't mention to you, that these invar strips here, straights, are 0.7 of a millimetre thick. Pretty thin. Again, I also didn't mention that with the Mark III system, the stainless steel plate is 1.2 millimetres. Sorry.
I'm curious about the welding here because we have dissimilar materials. So, are you using some components in the middle by metallic components?
No.
How do you weld the two materials together?
Right. Okay. There's a part of that I can answer and a part that I can't. The bit I can answer is the Invar tube is 1.5 millimetres thick, but it's made of Invar as well. So the connection from here, from our straight onto here, is simple because we're welding the same materials. The dissimilar bit comes from here, where we weld the Invar onto the anchor bar. Now the anchor bar is usually, in most shipyards, it's the same steel that we use for the bulkhead here. The type and method of welding, I don't know, because again, I'm not an engineer. I can find out, but I can't answer that directly, the type of welding that they use. I simply can't answer that. But whatever it is, it's obviously acceptable for welding the two dissimilar types of metal. But we don't use like bimetallic strips or anything like that. It's just welding directly onto that. So you might also perhaps think, well, what about the temperature? If this is at minus 160, because we've got liquid in here, and it's connected across through here, and this is ordinary steel, doesn't it like get it really cold? And the answer is no, because the thermal conductivity of this material is quite low. And because it's quite thin, at 1 and 1.5 millimetres thick, the heat transfer through it is very small. And so it's small enough that there's so little heat transfer through there that we can use ordinary steel here for that anchor bar. So it doesn't get down to sort of minus 160 or something at this point and crack steel. That's not a problem. So that covers the most complicated bit at the ends of the tanks where we're attaching this onto the inner hull. At the sides, again, because the transverse stretches are basically only thermal, then it's not such a problem. Now, we have two types here. We have in tanks 2, 3 and 4, where the sides are parallel. It's pretty straightforward. In tank 1, it's a little more tricky because of the angle, we actually have a combination of longitudinal and transverse forces. So we have to have a slightly different solution there. But if we look at this one first of all, because it's simpler, and then I'll show you the slightly more complicated solution here. So at these points here on the side, this is the arrangement. We don't have any direct attachment of the membrane onto the hull, but we do have these boxes here. And basically, we've got boxes that come up to the angle here, and we fill in the gaps with some small boxes and some small pieces of insulation in here. And to provide the continuity of the membrane, we have a small angle piece of Invar that's attached to the insulation here. And then our strips of Invar just weld directly onto those. So it's relatively straightforward. So remember, in the transverse sense, the only stress really is thermal. It's not a big deal. In tank number 1, where we have the angles, because we have this combination of longitudinal and transverse stresses, we have a slightly different solution here, which is referred to as a pillar, and this is attached to the bottom, to the inner hull. And again, very quickly, a little diagram here to show you the build-up. We've got a similar arrangement to what you've just seen, but these are attached to these pillars, so they cope with the longitudinal stresses. So there's the secondary boxes in place, there's the secondary membrane, here's the primary boxes going in, and then the primary membrane on top of that. So that solution deals with the combination of transverse and longitudinal stresses that you find in the forward tank. And in the corners where we get 3 surfaces meet together, well, it's like that tube wing that I just showed you just now, but it's got a kind of angle to it. So it's called a trihedron, but it's like the tube that you saw just now, but it's angled to cope with the change of direction there. So it's not, you know, it's complicated to construct actually, but it's simple to sort of understand and see how it fits. And once again, there's a very short little animation of just 30 seconds or so here to show you how that's put together. So starting with the inner hull, we have our box with the internal bulkheads, which would be filled with an insulating material. There's the mastic that goes on the bottom of the box, and the paper sheet that stops it from sticking to the hull. And then we're going to fit the box onto the inner hull, like that. We're going to fill in some gas. There's a couple of rods that hold the boxes in place. It has a spring washer in there. And we're going to fill in the gaps in a moment. That's the gaps filled in, and then we're going to slide in the tongues, the invar tongues, into the plywood box, then the straights of invar. So that's our secondary boxes and secondary membrane. And now we're going to fit the primary boxes on top of that. And then we're going to do a similar thing. We're going to put another tongue. There's a slightly different arrangement, but there's another tongue of invar goes in. That's just showing a couple of rods. So another tongue of invar will go in. And then the primary membrane goes on top of that. Okay, so very brief, but it gives you a little overview. Oh, here this is showing the insulation being filled with the glass wall rather than the perlite. Okay. And this is one of the options you can for reinforcing this system. We can fit double tops to the boxes. We can increase the thickness of these internal bulkheads. There's a variety of ways in which we can reinforce these boxes if we need to. But remember, every time you reinforce it, you reduce the thermal efficiency because you're putting more material in there. Okay, so you only reinforce where you need to. So yeah, that's the NO96 system. Very quickly, I've got a couple of slides left just to show you the evolution of that NO96 system, which is being referred to or being called the NO96 Max. So again, look out for this. You'll see and hear more about this in the near future in the shipping press. So let me just try and show you here. So this is a little diagram to show you the relationship between thermal conductivity getting worse and strength getting greater here. So with the normal NO96 with the glass wool, these are the reinforcement options. There are different names for them, but basically what I was telling you is as you reinforce it, your strength gets greater, but your thermal insulation, the thermal conductivity increases, so your thermal insulation is worse. So with the NO96 Max, what they've managed to do is have overall a better thermal conductivity and be able to improve the strength without reducing the thermal conductivity in quite the same way. So how do they do that? Well, basically, what they've done is they've taken the plywood box concept but scrapped the vertical bulkheads that you saw in the boxes, because if you apply sufficient force to that box, it can collapse the bulkhead in there. So what they've done is replace the bulkheads with pillars. Pillars are much stronger structurally. So they've selected a particular material. It's not the same plywood, it's a different type of material, but it gives a massive increase in strength. And as I'll show you, it has a slight advantage as well in another way. But this diagram shows you, it's like, think of the box that you've just seen, but take away the sides of the box and the bulkheads in the middle and replace them with a series of pillars. So you're getting a stronger structure, but still with a greater insulation performance. And the reason for the greater insulation performance is because there's less material in here. About 10% of that box structure was the bulkheads, was the plywood, you know, so that's all channels for heat transfer to go through. So if we look at, so here it's saying that here, with the old box style, 10% of the material, of the volume of the box was the material. Now here, if we switch to this pillar arrangement, then we can reduce that from 10% to 3%, which greatly improves the thermal conductivity, and at the same time is actually structurally stronger than that original bulkhead design. Now you have another option with this as well, Whereas if you want additional strength, if strength is the main criteria that you're after, what we could do is put more pillars in, so we can end up with the same percentage of material in there as we have here. So thermal conductivity is about the same as this one, but strength is much, much greater. So again, as the ship owner, you can choose which of these two options is going to be most suitable for the vessel that you want to build and the purpose that you want it to serve. So that's called the NO96 Max. And this particular system is also still going through approval from classification societies. But again, by I think 2017, they hope to start building the first vessel using this system. So if you look out in the press and the shipping press, you'll probably hear of this system used in the not too distant future. But once again, you heard it first here. Okay. So unfortunately, as I said, that didn't allow me time to go through the actual construction stages in the shipyards for these two systems. But to be honest, that's probably more than what you needed. Just having an idea of the concept, of what it's made up of, is hopefully good enough. And I hope that answers the question as well about does the membrane go all the way round, you know, on the bottom and the side. It's the same all the way round. Uniform all the way around. The only thing that varies is the amount of reinforcement at different areas of the tank, but the actual containment system goes all the way around. So that pretty much brings me to the end of the presentation that I had this morning. If you have any, I realise I've overrun by a few minutes, but if you have any questions, feel free to ask them now, or if you want to, you know, everybody goes and you want to hang back, that's fine too.
I think we are learning students. See any? Yeah, if you have, yeah.
Is there any guarantee if you position your design Mark 5 or the MO9 Max guarantee to testing that it's not necessary to be the operation of it?
I'm not sure I understand the question. Is there any guarantee that...
Actually, based on your experimental data, have you get any result for up to certain capacity of the power containment system is not necessary to consider operation of limits?
Ah, you mean like the size of the tank with maybe things like the sloshing issues and stuff like that?
Yes, not necessary.
I think the answer to that is there's no size or value I can answer that with, but what I can tell you is every time a ship project goes ahead, so a ship is ordered, GPT will conduct a study for each individual ship order to determine how much reinforcement is required for that particular containment system in that particular vessel for that particular size of tank. So it will be on a case-by-case basis. And so then you could say, right, okay, for this size vessel that's going to do work in this kind of environment, then we can reduce reinforcement to a certain level.
Is it practically possible to have a 10,000 emitters without consideration of operation? Is that because they're very large ships require?
Well, again, there are actually membrane LNG carriers with a capacity of 18,000 cubic meters. I suppose there's one a bit smaller than that, but not too far from what you just said. So in that particular vessel or class of vessels, they were built a long time ago, about 30 years ago, and they actually do have the similar operational limits imposed on them. But that was more because at the time there wasn't so much research and understanding. If you ordered one today, then a new study would be done for that vessel, and then they would say whether or not, you know, what the limits are. The limits might be a wider range of limits, or they might say, hey, you can fill it any way you like, and it won't be a problem. But they do it on a case-by-case basis, rather than saying, hey, if you go to this size, then you don't need that. literally done on a case-by-case basis, because it's not only the size of the vessel, it's how you intend to use it, for what purpose, and where in the world. Do you want it for worldwide trade, or do you want to only operate it in a particular location? So really the answer is, maybe it doesn't sound such a good answer, but the answer really is it's a case-by-case analysis to determine whether or not you have any of those limits. Okay. Any other questions?
I'm looking at.
They've all gone for lunch.
No,
They've all gone for lunch.
they say no thanks, no thanks. I think they are pretty much happy with what they have seen. What time is the flight?
My flight is 2:45, so I really need to get away.
20 minutes from here to the airport.
Yeah, so say I want to be at the airport absolute latest 2 o'clock. So,
okay.
I mean, ideally a little bit before that, because you never know how long the taxi is going to take. So, okay. I probably need to leave here by about 20 past to 1:30, I guess.
Okay, so we can have a lunch.
We can have a short lunch if that's okay.
Yeah, that's fine.
But, yeah, so that's my sort of limitation.
Okay.
So, guys, thank you very much for your attention. I hope you found it useful. And there is I think I can probably leave you, there's not so many of you, so I've got a card here. So up until, well, about the 28th of this month, you can contact me here on this email address. And after that, I'm afraid you won't be able to get me on this, because I will be ending my contract. You can certainly contact me up till then. And feel free to contact, I mean, the GTT themselves are always keen to try to help. So, yeah, like I said, I hope you found it interesting, and I hope it's of use in the wider projects that you're involved in. And, you know, I think LNG is a fascinating area to be involved in, and at this point in time, when there's this move to LNG as a fuel, and all the issues that go with it, from design to actually operating bunkering systems and safety and crews and all the other issues, there's so much stuff going on. It's a really interesting time to be engaged with the LNG industry. So I hope you, wherever your futures take you, I hope you'll find that interesting.
Sure. Is there any record to the application of membrane system for retrofitting of existing vessels? I'm sorry. Not for very beginning of the design. Existing vessels, the currently involving in the vessel